So when we're looking at this material, we see a cubic isotropically inelastic material that's metallic mold, that is in a metallic mold with lubricated rigid walls and open at the top. So the temperature of this system is increased from room temperature to 400 K. The thermal expansion coefficient of the polymer, so we know it's a polymeric material, so my Young's modulus is 1 GPa. My Poisson's ratio is equal to 0.4. And I increase it from room temperature, so 298 K to 400 K. And I'm pulling the system, again, rigid walls, but it's open at the top and bottom, and I have this, stress here. So I got my thermal expansion coefficient right here, and I've given quite a few other values. But let's go ahead and look at the stress state first. So I know I have a stress in the 3-3. My strain tensor, I know I'm going to have a strain in the 3-3 as well. I'm increasing the temperature of my material. So as I pull here, it is going to contract, but the material is also going to want to expand in this direction, and also in this direction, and this direction. Now, we are going to have to kind of calculate and see, is that going to eventually lead to any, expansion? But this stress kind of makes me feel that we're going to have basically nothing else in here. So let's go ahead, let's try to solve that one first, that conundrum. Let's see if any of the strains are positive, and then let's go at it. So I've got my y is equal to 1 times 10 to the 9. My nu is equal to 0.4. My g is equal to, again, I'm not sure if we're going to need this, but just in case, 1 plus nu. And then, so we got those values. We're also told that we've got sig 3.3, set it equal to, 587 MPa. So 587 times 10 to the 9, or 10 to the 6, excuse me. And yeah, let's go ahead, and we also know our alpha is equal to 108 times 10 to the minus 6. We also know that our fracture toughness, K1C, is equal to 189 times 10 to the 6. And strain energy release rate, G sub C, is equal to 87 joules per meter squared. And finally, the surface tension, my gamma, is also equal to, 87 is also equal to 189. Great. So there we go. And now we can go ahead and continue. So let's go ahead and get all these values in here. And now we can go ahead and start to tear apart and actually figure out what's going on in this problem. So actually, let's go ahead and we can calculate, let's go ahead and calculate some of these stress tensors as well. So I got my sig 3.3. I know I'm going to have a strain in the 3.3. I'm going to assume that this stress is going to be larger than the one of the thermal expansion coefficient. So let's go ahead and let's assume that there will be a stress, or actually a strain in the 1.1 and a strain in the 2.2. And basically those are going to be all our unknown values. So we know sig 3.3, so let's go ahead and let's solve, and let's just make sure if we get a value that's positive, then we need to kind of set that boundary condition to 0 because of those are rigid walls for basically the 1.1 and the 2.2. So let's go ahead and solve this just like we did for our typical problem. So we're going to say that, we're going to also say that we know we're going to assume sig 2.2 is equal to 0, sig 1.1 equals sig 2.2. Let's put those values in. Let's hide all the outputs right now. So E11 set equal to 1 divided by y times sig 1.1 plus, actually minus nu times sig 2.2 plus sig 3.3. And then we know the procedure from here on out. Copy and paste. Change, here, solving for E11, E22, E33. I have to change my values here, E22, E33, sig 22, sig 33, sig 1.1, actually, sorry, let me undo that, sig 1.1, sig 1.1 here, 3.3, and now we can go ahead and solve. And we do see, in fact, actually what we need to, we almost messed up, add our thermal expansion. So we should go ahead and look at the problem here. So we're increasing from room temperature to 400 K. So we've got our alpha, our del T is equal to final temperature of 400 minus 298, and then our ET is equal to alpha times del T. Let's get that. Then let's add that ET. Again, not phone home. I know, bad jokes. But this is one of the last videos I'll have to suffer that. But so we still see, again, strain here is positive, makes sense, and then it's negative in these directions, even accounting for the ET, so we're good to go. So if this was positive and it expanded, then we'd have to actually change our assumptions and we'd get different values and actually we'd have stresses. So we're good to go here, so we can kind of, so really we're only working with a uniaxial tension test. Fantastic. So the material is also represented by the red curve. So the red curve has a yield strength of about, let's say like 75 MPa. So I'm going to go ahead because I'm going to just draw. Let's zoom in here. Again, we could do a much more robust kind of calculation, but I see it's kind of linear, then like off. So like, 75 MPa. Good estimation. So I'm going to say that my sig y is equal to, and again, you could actually calculate and estimate a slope as well if you wanted to, but I don't want to do that necessarily. So, and actually you can't because you're not given the value of strain here. So we don't want to deal with that. So sig y is 75 times 10 to the 6. And now we should be able to go. So let's see what the question is actually asking us to do. So what is the size of the plastic zone? So we actually know an equation that relates and gives us our radius of plasticity. So the radius of my plastic zone, RP, actually, are we giving any information on any crack size? Not quite. So our RP is going to be equal to our K1 squared over 2 pi times sigma y squared. Now, K1 is equal to, K1 is going to be equal to our sigma square root of pi a. Now, one of the things, we could just solve it as so. So for example, I know, actually, wait, so I could set that, for example, K1 is equal to sig times square root of pi times a. In this problem in particular, now I could set that my RP, set it equal to K1 squared, divide that by, again, I'm a parentheses person, you don't have to do that, over 2 times pi times sig y squared. So you can see our value is a function of sig and a, but the sig that we're applying here is sig 33 in this problem. That's for sure. Now you have your radius of plasticity as a function of your crack size a here. Now, if we wanted to calculate our radius of our plastic zone basically at the point or at the critical, crack size for fracture, we can use the following relationship. We know K1C, and we know that K1C, and actually we could solve for, we know that K1C, set that equal to sig 33 in this problem, again, because that's the stress that we're applying, times the square root of pi times a, and we could solve for that numerically. So this would be my critical crack size for failure. So I could set that AC is equal to this. So I could also do, for example, this is my radius of plasticity in general. I could also solve it in terms of, this is the general expression for any room crack size, / dot, and then A goes to AC. So you can see that as well. So 1 meter. So that's a pretty large value. But again, these are my made up numbers. What is the critical crack size for failure for the stress rate? We already calculated that. Just for fun, we already did it just in case. Is this material yielding? If so, via what yielding mechanism? So are we yielding here? So let's see. So if we go from, actually if we go by our ranking criteria just says, is sig 33 greater than sig y? Yes, so we are definitely yielding. Is sig 33 greater than sig y minus, basically sigma y? In our stress tensor, we only have basically one principal stress, so my sig 1 is equal to sig y, my sig 2 is equal to 0, my sig 3 is also equal to 0. So if I do my Tresca criterion, is sig3 greater than sig1 minus sig3? Yes. And if I do my von Mises, it's the good old gigantic monster square root of 1/2 times sig1 minus sig2 squared plus sig2 minus sig3 squared plus sig3 minus sig1 squared. That's my effective stress. Is this greater than, or is sig y, or is this greater than sig y? That's what we're saying here. Actually, let's see here. So actually, let's do. This is sig y. Excuse me. Yeah, and then is. Actually, so let's do. Actually, here we go. Let's just be consistent here. So we're asking, our condition is if sig1 for ranking is greater than sig y, then it fails. Then it's where's our sig1? I think our sig1 is a little bit off. 87, 6. I think we may have a little bit of a definition issue here. Oops. Sig1 should not be this. Here's my problem. Excuse me. Apologies for that. So, is sig1 greater than sig y? Yes. So we are yielding. Is sig1 minus sig3 greater than sig y? For sure, yielding. And then, is my sig effective greater than sig y? Greater than sig y. Oops. So yeah, we are definitely yielding. That's a huge stress. Excellent. So that's it. So it's been a pleasure to have you all in class, and I hope to see you again soon. Thanks. Have a great day. Bye.